I want to thank everybody for coming. The title of this talk is Clojure Made Simple. On the brochure, they left out the comma. So it's not Clojure Made Simple, in other words, a tutorial on Clojure or an easy explanation of Clojure. It's not actually a comprehensive explanation of Clojure at all, but I'll look at a slice of what Clojure is about and a way of thinking about why you might want to use it. So I'm the person who made Clojure. I currently work on a database called Datomic, which is kind of a functional database. It's written in Clojure and runs on the JVM architecture. I'm a co-founder of Cognitech, which builds Datomic and sponsors the development and stewardship of Clojure. But the main point I wanted to make about myself to this audience was because in this talk I might seem somewhat skeptical of Java and object-oriented programming, is that I've done an absolute ton of that. That's what I did for 2 decades before I said, if I still want to be a programmer, I don't want to do it this way anymore. So I know exactly how apps are built using Java and C++ and C#, because that's what I used to do. That doesn't mean what I think about them is correct, but that's my experience. But I'm wondering about you. How many people program in Java here? How many people are happy about that? How many people are actively unhappy about that and looking for alternatives? Okay, great. How many people have tried Clojure at all? Great. How many people have never heard of Clojure and are in the wrong room? Okay. How many people have tried Clojure and are trying to get it to use it at work, but not yet? A few. Maybe this talk will give you some ways of talking about Clojure's value proposition that could help you. How many people actively use Clojure and somehow are accidentally at JavaOne? Okay. And the rest couldn't get into Brian Getz's talk. I shouldn't even mention that Brian Getz has a talk right now because we could have people filing. Or maybe you're just tired of Brian Getz talking about immutability, in which case you're definitely in the wrong room. No, I like him. Brian's a good friend, and his talks are great. So I appreciate you bringing this one. So there were very few people who had never heard of Clojure, so I'm not going to spend a lot of time on it. Oh, I had one more question. How many people have seen my talk, Simple Made Easy? How many people have not? Okay, a few. So I may spend a minute describing what I mean when I say simple. Clojure is a programming language. It runs in the JVM and JavaScript. And pretty much a substantial subset of Clojure runs on JavaScript. So it's a programming language with which you can target both. But originally it only targeted the JVM and the CLR. There's still a port to the CLR that's maintained, but does not see wide use. I released it first in 2007. It's had, surprising adoption, especially from my perspective since then, given its characteristics, because it's a Lisp, it's functional, it's data-oriented, and it has a lot of things that make it seem not like the kind of language that would succeed. And this talk will really be about the data orientation of Clojure. So, a lot of the best programmers and the most productive programmers I know are writing everything in blank and swearing by it, and then just producing ridiculously sophisticated things in a very short time. And that programmer productivity matters. So Adrian Cockcroft was cloud architect at Netflix. Now he's at Battery Ventures. How many people think Java goes in the blank? Okay. So we know this. There's something about Java that makes it not suitable for this blank. So maybe we can tease that apart. Yes, of course, he was saying Clojure. And this talk is about maybe why. How could this be true? What is it that makes Clojure different and possibly a better fit for that blank? So the first thing I want to talk about is that I think we have this tendency in programming to think about ourselves just a ton. And our languages and our tools and our techniques and me, us, what we're doing, whatever. We lose track of the fact that we're all working for somebody else or ourselves, but for a business or an organization that's trying to accomplish something in the world. And the software is completely secondary to that task, right? It should be measured always in terms of the cost-benefit ratio, the return on investment, right? How quickly can we get a product to market, and is what we're doing profitable, right? If we're not doing that, we're not really being good participants in our businesses or organizations. So what do the stakeholders want? They really want two things. They want something good, and they want it soon. So something good, we think we know what's something good. We know how to make things good, right? We have these techniques, and some things are good when the techniques are successful with them, right? So when our types check and our tests pass, we have something good. But of course, we all know that with our best efforts in those things, which I'm not saying they're bad activities, by the way, but no matter what we do there, we end up with programs that don't work. We all know we have programs that type check and test pass, and they don't work. And they don't work from the perspective of the stakeholder. In other words, they don't do what the program was supposed to do, and that what's supposed to do was something that was conveyed between people or through documentation or papers or things that are not in programming languages. They have to meet operational requirements, and they have to be flexible. Okay? Now, there are some times where people just want something soon, and they don't want something good. There are actually better languages in Clojure for that. Right? Just give me something fast that I'm absolutely definitely going to throw away, will not grow, will not expand, will not take me further. So these first two things are means, right? They're good, but they're only good insofar as they help ensure the latter three things. So if we break it down, what is it supposed to do? Again, it's a perspective thing. If the stakeholder thinks it's doing what it's supposed to do, they're fine. Now, of course, they're going to have expressed concerns about software. What it's supposed to do, it should do this when I push this button. And they're going to have unexpressed, presumed things like it should be secure. It shouldn't, cause the computers to go on fire because it's so slow. It shouldn't require 3 new data centers. It should keep running and not stop for an hour every day. Those are sort of the unstated presumptions of something being good. But it ends up that if you build large, elaborate, stateful programs, it's extremely difficult to ascertain whether or not they are going to do what they're supposed to do. And in fact, if you build any one of those things, if you just build a very large program or a very elaborate program or a very stateful program, it will be as hard to figure out if it's going to do what it's supposed to do. So one of the things Clojure is oriented at is making it easier to understand whether or not your program is going to do what it's supposed to do, mostly by making it substantially smaller and also by making it more functional. In terms of operational requirements, there's a boatload of things. There's a boatload of unstated requirements of software. Two are, can I deploy it in the normal way with all my stuff, with the people who know how to run my machines and everything else. And that's one of the targets of Clojure. Clojure was meant to be hosted. It's just a jar. It runs in the environment. It's easy to sneak in, right? It's just, I have this one more jar. And then we're running. But it's not a small thing, right? If you wanted to adopt Common Lisp, say, or Haskell, you'd be asking your ops team and your deployment team to start manipulating something completely alien, whose characteristics they don't understand. In terms of security, everything that's available from the JVM for security is available via Clojure. And then performance and other concerns. A very important thing, though, is that now we can also reach the browser. So I think, how many people write applications where some part of the overall system touches a browser? Yeah. So right now you use two different things. Right? Almost definitely you use two different things. And I think it's a strength of Clojure that we're delivering the same value proposition in both places, both on the server and in the client. Even if they're separate devs, the value proposition is necessary, and almost more so in the browser, which is one of the most complex places ever. In terms of performance, a lot of times you might look at a dynamic language and say, how could it be whatever? But, Clojure's right down there with the fast languages. On, admittedly, the benchmark game, which is a benchmark and a game. So, but it says we can reach that. On JavaScript, we have a very interesting result here. So Ohm is a ClojureScript library. So ClojureScript is Clojure on JavaScript. And Ohm is a library that actually wraps React, which is the new hotness. What's the really interesting things here? Ohm wraps React and then spanks it in performance. How is that possible? It ends up that Ohm's use of persistent data structures, which I'll talk about in a minute, Make it faster than React, because the big part of React is doing change detection, and change detection for immutable things is identity comparison. So it's super fast. And in fact, they are re-architecting their whole thing to use persistent data structures in JavaScript now. The React dev came up to me at Strangeloop and said, shook my hand and said, you're saving us a ton of money because we're switching to that strategy. So the other part of the value proposition I said was flexibility, right? People that have a stake in software know that they're building a system now, but tomorrow things are going to change. Requirements are going to change. We have to do something different. Change is inevitable. So can we change the program? Can we make it more flexible? And it ends up there's a lot we can learn from bigger system design in the small to make the subcomponents of systems more flexible. And of course, this is the oldest thing, right? Loose coupling, right? But we talk and talk and talk about it, and we continue to use techniques that thwart it. Like every single day, you pull out a technique, you do something that makes this harder. So what makes it easier? My talk was done, and somebody said, I have this quote from Walmart Labs guy. You might want to put it in your talk. And it was like, wow, this is great, because he's telling my story. Right? With Clojure, we get to market faster and with better quality. We avoid unintended interruptions in Java apps when code in one area impacts the application in another. Clojure shrinks our code base to about 1/5 the size it would have had we written in Java. Right? And these are the points of my talk. Right? This is what I want. This is a stakeholder saying, this is what we get by choosing Clojure. Faster time to market, better quality. Right? We avoid coupling problems that make it difficult for us to change. And we have a smaller code base. So how does Clojure do this? There are many, many different characteristics to Clojure, but I only want to talk about sort of two today, mostly one. One is, and because this is one I think that sets Clojure apart, it makes it somewhat different, is that it has data orientation through and through. And the other is simplicity. So when I say simplicity, I mean the opposite of complexity. I do not mean ease. I don't mean Clojure is an easy language. That's easy, you type and everything magically happens. There's some sort of easiness metric. Complex things are intertwined and simple things are not. Right? They're more independent. They're separate. Even if they have as many things going on, this is simpler than this. Right? 4 things like this is complex, and 4 things like this is simple. So that's what I mean when I say simple. Unentangled. So the thing is that, all these languages can do everything, right? We can do the same stuff. And people are like, well, I know I can do the same stuff in C# and Java and Scala and Clojure and, any general purpose language. You can accomplish the same things at the end of the day, right? So what differentiates languages is what they make practical and what they make idiomatic. And in Clojure, we focused on making something idiomatic that I think is not and should be more so. That's this. Before we had all this highfalutin, opinions of ourselves as programmers and computer scientists and stuff like that, programming used to be called data processing. How many people actually do data processing in their programs? You can raise your hands. We all do, right? This is what most programs do. You take some information in, somebody types some stuff, somebody sends you a message, you put it somewhere, later you try to find it, you put it on the screen, you send it to somebody else. That's what most programs do most of the time. Sure, there's a computational aspect to programs. There's quality of implementation issues to this. But there's nothing wrong with saying programs process data, because data is information systems. I mean, this should be what we're doing, right? We're the stewards of the world's information. And information is just data. It's not a complex thing. It's not an elaborate thing. It's a simple thing until we programmers start touching it. So we have data processing. Most programs do this. There's very few programs that don't. Right? And data is a fundamentally simple thing. Data is just raw, immutable information. So that's the first point. Data is immutable. If you make a data structure, you can start messing with that. But actual data is immutable. So if you have a representation for it that's also immutable, you're capturing its essence better than if you start fiddling around. And that's what happens. Languages fiddle around, right? They elaborate on data. They add types, they add methods, they make data active, they make data mutable, they make data movable. They turn it into an agent or some active thing. And at that point, they're ruining it. At least they're moving it away from what it is. And in object orientation, I think this is rampant because our fundamental construct, the object, conflates two things. It doesn't give us two separate ways to talk about process, for which objects are an okay approach, and information, for which they're a terrible, terrible, terrible approach. Right? But every time we have a problem, we pull out an object, we make a new object, we make a new class, we make a new instantiation of something. Right? And this makes our programs more about themselves again, and less about the information. Programs are more increasingly about code and decreasingly about data, and I think that's a mistake. So Clojure embraces data. That's like the simplest idea behind Clojure. It's just, there's nothing wrong with data. Data has these great properties. Let's use it. In fact, let's make it a really important first-class, in-your-face kind of thing. So Clojure embraces it first and foremost by having strong data literals, which I'll show you in a minute. And they're plain. Right? Plain, it just means flat, level, unadorned. No extra stuff. Right? Code, and this is an old Lisp thing in Clojure, is represented as data. That's important for a lot of reasons. It enables macros and a lot of sophisticated program transformation things, but it also means that you don't have different stuff. Right? The majority of functions in Clojure just take data, and by data I mean immutable, unadorned stuff, and they return that same thing. Giant library of functions, hundreds and hundreds and hundreds of data manipulation functions. Ready to go, they take data, they return data. So if you have anything that's data, you can use all those functions on it, which tends to press you towards making everything data. Because then you have this giant library which you learn once, and you can apply to every problem you have. And in particular, every time we encounter information in Clojure systems, because there's different parts of systems, right? There's a part of your system that manipulates information. There's a part of your system that's sort of plumbing, right? Or the machinery of your program, like a socket or a communications endpoint is more like a machine than it is like information, right? So there's going to be active parts of your program. But whenever you're dealing with a part of your program that's just about representing facts and information, we will always in Clojure choose plain data to do that. So there's a small set of data literals in Clojure. They're relatively obvious, right? You can write integers in the normal way and doubles in the normal way and big decimals with an M at the end. There are ratios, and these are proper ratios that don't lose precision. Strings are in double quotes, and strings are Java lang string. When you write that, you get a Java lang string. It's just a literal for a string. There are literals for characters. Because we use data structures for programming, right, there's a couple of extra things we need. But if you look at Java code, is it written all with quotes around every word? No. So Java needs something besides strings in order to be a successful programming language. It needs symbols. And it needs identifiers. So if you're going to properly represent your code as data, those things have to be first-class data structures or atomic data types that are different from strings. So there are two in Clojure. One are symbols, and the other are keywords. And their use in Clojure, which I'm not going to dive into, is that symbols are generally used to reference something else. So like variables and things like that. They name something. And keywords name themselves. They're more like enums, if you want. They're very useful as keys in maps, for instance. And that's why they're called that. There are true and false Boolean literals. And there's nil, which is null. And it's the same, that's a Java null. And those Booleans are Java Booleans. Those characters are Java characters, et cetera, et cetera. And there's also literals for regex. And then we have data structures, some fundamental data structures. We have the singly linked list, right? It's in parens. Those are all lists there. List of numbers, a list of symbols, a list that has a symbol and then some numbers. That's okay, can be heterogeneous. And they grow at the front, and they have linked list kind of performance characteristics, which means it's fast to put something at the front, and it's slow to find the 57,000th thing. It's linear time to find stuff in the middle. Then we have vectors, They're in square brackets, right? Again, they can be heterogeneous. This happens to be one with numbers and one with symbols, but you can intermix them. They grow at the end in constant time, but they also offer fast access anywhere in the middle. So they're different from linked lists then. And then there are maps. They're key value, key value, key value. The commas are optional. The keys need not be keywords. So the first one uses keywords mapping to integers, and the second one uses integers mapping to strings. But you can be heterogeneous in both the key and the value. And then we have sets, which are just curlies preceded by a hash. And you can have sets, again, heterogeneous of anything. And all of the stuff nests. One of the important things about this is that these maps, they scale and are efficient from the very small all the way to the very large. So you can use them as sort of pseudo objects in the small and have 4 or 5 fields, if you will, or entries, or you can have a giant map that has millions, tens of millions, hundreds of millions of things in it. The same data structure is used throughout that range in Clojure. We don't distinguish those two uses at all. So all of the data structures I showed you are immutable. There's no way to change them. Just like there's no way to change 42, there's no way to change a vector. What you can do is make a new vector that's slightly different from the vector you started with, and you have both vectors. And there's a technique called persistent data structures, which makes this making of a new, slightly different version efficient. The two versions will have a substantial amount of structural sharing going on under the hood. And that's possible because they're immutable, right? They can share structure because no one can change them. And that's what makes it practical to use immutable data structures all the way through the range, from tiny things through very, very large things. It's not copy on write, right? These new modifications that you make still comply with the big O expectations you have for the data structure in hand. And this is the key to practical functional programming, is having this. So the idea behind Clojure, or one of the ideas behind Clojure, is just this, right? I had done so much object-oriented programming, and it's just so much busy work and so much extra stuff. And when I finally, later in my career, learned Lisp, I saw people building very, very interesting systems out of much, much simpler stuff. And I tried it, and guess what? You can build exactly the same systems out of much, much simpler stuff. And I said, well, I can't repeat it. But I was very unhappy. Basically something to the effect of, I have been wasting my time and my career doing what I've been doing. And I need to do something. I need to change what I'm doing. Because I'm wasting my time. I'm wasting my life doing it this way. Because you can build programs, the same programs, better programs, that do the same things, with substantially simpler stuff. In fact, you can build them out of the data structures I just showed you, plus pure functions that take those things and return those things. Most of your program you can build that way. And little tiny bits of your program, you'll have state, you'll have communication, you'll have the other aspects. I like runtime polymorphism, and Clojure has it. I'll talk about it in a second. But you can build programs out of this, and you can build big programs out of it. You can build databases out of it, right? I've done it. I built a database out of it. When I made Clojure, I was targeting being able to do everything that I used to do in Java and C++. So I built broadcast automation systems, scheduling systems, yield management systems, election projection systems, and exit poll systems in all those, C++ and Java and C#. I believe that I could have used Clojure to build anything I ever built, right, with maybe a tiny little bit of lower level code in small places. But that's the target for Clojure. I wanted to replace what I was doing. I think the programs are substantially smaller, they're simpler, and they're much more robust than the object-oriented programming I was doing to accomplish the same jobs. So the idea behind Clojure is, let's make that idiomatic. Let's make that the first class way we do things. So the syntax of Clojure, there's no more. You just saw it. It is those data structures. That set of data structures and those fundamental things are a format called Eden, which stands for Extensible Data Notation. But it's just a grown-up version of S expressions, which have been used in the Lisp community for years. Basically, you build programs out of data structures. And I'll show you some of that in a second. So the data structures are the code. The syntax is not based around characters, it's based around data structures. The definition of what a function is a list whose head is a symbol called, fun, and whose next thing in the list is a vector of arguments, which are themselves symbols, et cetera, et cetera, et cetera. But the syntax is described in terms of data structures. It's not like there's no syntax, but that's where the interpretation happens. And everything that would be special in an ordinary programming language, declarations, control structures, function calls, operators, et cetera, they're all just represented as lists with the verb at the front. That's it. That's the Lisp way. Also, everything is an expression, and that's typical of functional programming languages. That's about all I'm going to say about Clojure, the language. But I'm going to show you a lot more about the use of these aspects of it. I have a little bit more later. So Eden, this extensible data notation, I showed you some built-in things. There's also a way to extend it to add new tags that are namespace that allow you to describe something new in terms of anything that's already known. So you can't make up arbitrary stuff. You can't say, well, build a new parser to parse characters and get this thing. But you can say, I have a new interpretation of a vector of 2 numbers, and we're going to call that a point, and so on and so forth. And you can cascade these extensions and build richer things. But one of the important things about Eden is it's meant to be useful as for data and code. So you saw in the previous slide, I said, commas are optional. That's kind of critical. Imagine if in between, in between everything you said in Java, you had to put a comma. Who would like that? That would be awful, right? So you can't have stuff like that. So, I mean, how many people have ever used any system that tried to encode programming in like JSON or XML? Yeah. How fun is that? Yeah. So this is a little bit of like AWS CloudFormation has some functions in their syntax, which is normally declarative. So this is a nested function call. But you can't do this, right? You can't program like this. So if you're going to program using data structures, you have to have a data structure format that's amenable to that. So this is what Clojure looks like. I don't really expect you to be able to read it. But I just told you before, that's a list, right? A paren. Define, right? It defines a function. The name of the function is words. It takes an argument called text, and there's the implementation. And so on and so on and so forth. So this is a port of Peter Norvig's Python code. It's as short as the Python program, right? And that's not like a contest, right? It's more about this. Everything that's in here is about the problem. Like all the words you're reading and everything, it's all about the problem. There's no extra stuff. There's no static import, blah, type this, type that, yada yada, extra control stuff. It's all about the problem, 100% about the problem. And that's what you want, right? So it's short, it's free of ceremony, but most important is it's about the problem, which means it's a lot easier to look at now and later and see what you're trying to do, what you're trying to accomplish. So once we have this format Eden and we use it for code, and we can obviously use it for data, you use it for everything, right? So let's say you wanted to have a DSL to represent HTML, right? Because we know HTML on its own is kind of gross to generate and manipulate because it's XML plus some randomness. So this is one of many DSLs for representing HTML in Clojure, but it's Eden. This is the same stuff that the program was made out of. The same reader reads this. If I call read, which is available a la carte in Clojure, I get a vector that has a keyword, then a vector that has a keyword, a vector, blah, blah, blah. I get data. I know exactly what I'm going to get, the data structures I'm going to get. I don't have a special thing. I don't have a DOM, blah, blah, blah. No, I get data when I read this. And that's great. It means it's easy for me to process this. It's easy for me to write a program that produces this. So I can produce HTML without an extra special different thing. Of course, we would use this for our configuration files, right? Why not? We can read it. We can generate it. We can process it. We can manipulate it. Everything we know, all those hundreds of functions we know how to do, we can use to do this. Now, add up the stuff in Java. How much have you got? You have syntax, for which you use, I don't know what, some parser thingy, right? From Java C or something to manipulate. You have annotations. Right? You have JSON here, you have XML there, right? Maybe if you're writing your own DSL, you use Antler or something. It keeps adding up more and more and more different things. And if you read stuff with an API, what do you get? Some API author's idea of the DOM for this kind of thing, right? What do you get when you read XML? Well, it depends on how you read it, but you could get this, machine, right? that calls you back every time it gets a new element. Wow. This is Hadoop programming. Netflix has quite profitably used Clojure to build a very succinct DSL for doing Hadoop and big data processing. It looks exactly like Clojure. It is Clojure. It's sort of embedded in Clojure. And the thing is, you can run this locally and then push a button, and it will distribute it over your Hadoop cluster and run it there. Same thing. And you can run your own Clojure functions there too, and they'll ship them and everything else. So we just do this. We do this everywhere we want. There's a type annotation system for Clojure that uses data. There's a schema language for Clojure that uses data. There are many kinds of logic DSLs that all use data as their representation. And this allows you to do something that's very interesting, which is to write an embedded DSL. Right? How many people have written a DSL and had more and more pressure to make it Turing complete and general purpose? Right? You started with the DSL and it did X and Y, and then people are like, could you do Z? Could you have conditionals? Could you have case? Could you have, they always want more stuff. So one of the cool things about doing DSLs in a language like Clojure is that you can sort of co-opt all of Clojure inside your DSL. It's like, oh, you want to do arithmetic? Well, sure. All you have to do is expose something, and you're gonna flow through to Clojure and let Clojure eval it. So it's very powerful. You keep doing this. The other big point of programs as data is it allows you to write program-generating programs, and that takes a few forms. In the small, there's a capability in Clojure and other Lisps called macros. They're nothing like C macros from your past, maybe, depending on how old you are. They're functions of data structures to data structures. But basically it says, the compiler for Clojure says, if you declare something as a macro, then if I see that in the program, I will call your code. I will give you the form as data that I encountered, and you give me back a different form. You can do any transformation you want. Which means you can build your own syntax. You can build your own constructs. You can extend the language however you want. You do not need to wait for me or for anybody else or for the Java JSR, whatever. You just go. So we're doing all this stuff with raw data structures. And how do we contrast that with objects? Right? This is the ranty part of the talk. Just warning in advance. So objects are like marionettes. Everybody has their burrito analogy, but objects are not like burritos. Objects are like marionettes. Right? They have all these methods on them. Right? And anybody who has access to the object, it's like they have that control stick thing. Wikipedia says that the person who has that is called the masterminder. I couldn't find anybody else who agreed with them, but that's a cool name. Like, you can remote control the object, which you can, right? If you have a reference to the object and you know its type, you can call any of its methods whenever you feel like it, in whatever thread you want, right? Just have at it. You can do anything you want because you can call those things. So whoever writes the object, the class, they have to defend against that, because what's going to happen? Well, in the real program, you're going to start passing around references to that object. Well, now you have more than one masterminder. Now you have as many masterminders as you've shared references to the thing. And anybody can call something at any time. And what do you end up doing? You end up saying, well, maybe they're friends and they're standing next to each other and they're like, okay, let's make the fancy horse, dance, and I'll do the front legs and you do the back legs. And that happens in puppetry, right? But in programming, sometimes they just go off, and like somebody's trying to make the front of the horse go this way and somebody's trying to make the back of the horse go that way. And it doesn't work. And so you have to have all kinds of protection. And you actually can't effectively do this. Java and languages like it don't give you an effective way to do this. So you're suffering from this constantly. As soon as you have a reference leak, you're suffering. Now, I know you say, I use value objects and blah, blah, but you don't everywhere. You could, but you don't. And it's not idiomatic, and it's still hard. And you still don't even know. Like, if somebody gives you a reference, right, to an interface, can you know that it won't start dancing on you? Is there anything in Java that will tell you it's not going to move around? Any way, any construct, anything in the type system, anything? No. Nothing. So every day you have this unhappy face. And then, right, the final problem. Right, Right? How many people write a program? It's just a program, and like it sits by itself, and it reads standard and it spits standard out. Right? Compiler writers write that stuff, right? And they write these great languages that are really good at that. Right? But that's not the real world, right? How many people write programs that talk to other programs routinely? Yeah, we do that all the time. How many people put objects on the wire? Wow, that is terrifying. All right, well, just so you know, a long time ago, we decided that was a bad idea. So I don't know if you got the memo or whatever, but yeah, objects don't travel on wires. You can fake it, you can pretend, you can make all these elaborate things, but most of these things have failed in practice, right? You can get away with it in small circumstances, but it's not how things work. Right? We don't actually give somebody a reference to something and allow them to sort of remote control us. Right? So, this is what I was saying before. If your API takes an object, especially via a reference to an interface, right? So you don't have the concrete class's definition to sort of make you feel better about it not changing. Do you know if it's going to mutate? Right? Can your type system help you with this? Which is really, it's such an important thing for the robustness of your program to control this. And the answer is no. You're getting no help at all. So your default idioms leave you completely on your own to deal with these problems, and really in a position that encourages you to create these problems just by accident. Right? The other thing is, so let's say RMI is not allowed at your company. How many people are not allowed to use RMI at their company? Everybody's allowed to use RMI. Wow.
And we're allowed to use GoTo as well.
GoTo, yeah. That's actually not as bad. But let's say you're allowed, right? And somebody says, I want you to server-size your thing. How many people would choose RMI over something else, like HTTP or anything else? Right? Nobody would, right? And then what do you have to do? Right? You have this interface. You said I took an object. I expected all these methods on the object, and now I have to talk over a wire. What do you have to do? Mapping, right? Object relational mapping, object blah map, object something map. Every time you want to get to and from the outside world, especially stuff you're not writing, so RMI is out of the question, right? You're not going to get like some website to like accept your RMI calls or make RMI calls to you, right? Anytime you have to go outside of your box, out of your worldview, your object worldview, you have to map, right? So, Java programmers and object-oriented programmers have been like, kicking SQL, saying, oh, it requires object relational mapping, and that's like a problem with SQL. No, it's a problem with objects, right? Objects are not the way the world works. Nothing in the world works that way. People do not hand their strings out to other people to like start yanking on them, and like that's how we're going to build this. That's how we're going to have like a soccer team, right? It's like everybody's going to have a reference to somebody else, and like you call pass to me, and like we build this big spaghetti nightmare. That's not how the world works. It's completely not the way the world works. It's not how physics works. So we say objects and their way to model the real world. It's not at all. It's a complete programming fabrication. It's not very realistic. It's not a good fit for almost anything that's in the outside world. So you can build your own world where all this stuff makes sense, but it's inherently, I would call it idiosyncratic. But in particular, it's not the way that systems work, right? Systems in the large, right? So what are systems? Well, the word system means to cause to stand. And I love that idea. I mean, I always think of like these legs sort of self-assembling to try to make something that stands up. There's independent parts that you connect together, substantially independent parts, right? Because you don't need to cause something to stand that's like one thing that already has three legs. You're not causing it to stand up. It's the independence of the things that matters. And in general, we try to build systems in a way that makes them independent, right? Do we want to care if another server is using the same programming language that we are? Or the same runtime, or the same version of the Java runtime, or the same type system? Do we want to build a system like that where we care? No, we don't. Why? Because it's going to be brittle, right? It's going to be hard to make changes. We're going to have to agree with the other person, right? Tomorrow, we're going to have this thing, and everything's going to be different. 3, 2, 1, We don't do that. The internet, does it work that way? No, right? we don't do specific stuff. We do general stuff, and we try to be as independent as possible. Most things that happen between systems use one of two techniques, right? They use RPC with plain data out and back, or they use queues where you send data and somebody shows up later and gets the data. You just send and you just flow data around. This is the way that systems are built. Big systems, big successful systems like the internet, and most systems. Right? And those systems are flexible. You measure their flexibility in terms of how much independence they support. Can you independently develop these parts of the system? Can somebody upgrade their part of the system and not mess up the other person? Right? Because like Twitter is not going to tell your web browser when they change their homepage and like have Safari, do something special. That's not how it works. Right? Everybody has independent development, independent time frames. And then the other thing that's critical to this is that if somebody else on the other end is going to change, you have to be tolerant of things being different. Right? You can't say, well, here's our contract. There's 900 things that have to be exactly this way, and then I'll work, and then you'll work. And if we're going to change anything, we have to, have lunch and have a meeting and decide this stuff again. You have to be tolerant in accepting some more things. So we don't have to change in lockstep. And so these systems are inherently dynamic, and they're inherently extensible. Right? That's what I just said. Systems are made with dynamic types, extensible types. Right? They can accept data they weren't expecting to see, and it won't make them fall over. And hopefully they'll do a good job of propagating it. Right? They're all made this way. So this is the other fundamental idea of Clojure. We should build the insides of our systems like we build the outsides of our systems. All those value propositions that accrue to systems, we want them. How many people want to have a meeting every time they change a class or a subsystem? How many people have meetings every time they change a class? Yeah, you have to, right? This is going to break. Stuff's going to break. So we should communicate using immutable data inside our systems for the same reason we do outside. It makes our systems more robust. It makes them easier to change. It makes the independent parts separate. It makes it easier to move them around. Right? We get loose coupling, we get subsystem independence, we get flexibility. And what's the mapping? Well, there's no real mapping, right? This doesn't need mapping. Right? RPC becomes PC. Right? We can call functions. We were calling functions before there was R, right? Then they had R. We had PC before we had RPC. We can go back to PC. We can do that. Right? We can pass data to functions and get data back. We used to be able to do it. Then we had all this elaborate stuff. Now we forgot how to do it. Right? And we can implement queues and flow inside our programs using queues or channels or things like that. So that's the other key idea. Now, there's going to be process and state. Right? Clojure is a practical language. Of course, you're going to have process and state, or there's no reason to run your program. Right? Just make the computer hot and you go home. Right? You're going to have state and effects. But this is another area where we're left just totally with nothing in object-oriented languages like Java. You have nothing here. Right? There are very fancy functional languages that have purity. Well, they will force you through the type system to identify and isolate all the parts of your program that could do I/O or have any kind of effect. They'll either do it via purity or via effect systems. Right? And then there's the alternative to that is nothing. Right? So most people have is absolutely nothing. And then you could also have reified constructs that at least make state change explicit. And that's where Clojure sits. Because in Java and C++ and C#, you have nothing. You basically have nothing. You have some really raw constructs like mutexes and a pat on the back and good luck, buddy, and read Brian's book. So Clojure doesn't have any purity to it, but it has explicit constructs for state. These are like, you can imagine them being variables that have semantics to them. So it's not just like anybody can come in and whack on this variable at any time. Instead, you say, I'm going to give you a function, and you somehow apply that function to that variable to move it from one state to another. But in doing so, you can ensure it's free of conflict and free of races, and it's never going to become half of a thing. And these variables always refer to values. So you're always able to observe them or dereference them and get out a value. There's nothing else. There's only these reference cells that point to values and values. There's no mutable object, the half of which could be whatever, or like a date class that you could set the month or things like that. Right? A date is a value. You could have a reference to a date, You can make that reference point to another date, but you can't change a date. And so you have things you can change, which are references, and you have values, which are not. You can't change dates anymore. You can change 42, right? But you can change these references, but they're atomic. They just point to one thing. So between those, you can get a whole bunch of different variants, right? CAS implements a successorship model. You say, only make this new thing if it was this thing if my presumption is still valid. Right, so that's the tiniest version, and Clojure has a construct that wraps that. So you don't have to write the loop or anything else. You say, here's my function, apply it to the inside of that, use CAS, do the loop for me, and I know I'll get a clear successorship there with no race and no conflicts. There's also an STM in Clojure that allows for bigger transactional kinds of modifications to occur. But the point is, this construct is doing the job, and the construct is calling out, here's where the mutation is in the system. Here's where the state is. And the thing is, you have a way to get out of it. Right? If I give you something that you don't know if it's going to change, how can you save its value? Like if I give you a reference via an interface to some composite type, you don't know if it could mutate, how can you save its value? What's the safe way to do that?
Clone.
You don't know that clone is going to work at all. Sorry. Does not work. What else? Walk through all the gets, get this, get that. You got nothing. You have absolutely nothing. So this is like a critical thing for making a system that works. You have absolutely nothing to do this with. Right? You have to build up your own convention around this. So I think you should pick. Right? You should either have explicit constructs or go all the way to Haskell, because everything in between is catastrophe. And then we have, in Clojure, we have something called core async, which is a channel model. It's a little bit richer than queues, because you don't have to set up the threads and do all the micro writes. They have semantics that are based around something called communicating sequential processes. But the basic idea is that you're going to try to encourage, especially when you're trying to convey values through a system, instead of saying, I'll put the acorn behind this tree and you come by later and find it behind the tree, you say, I'm going to put the acorn on the conveyor belt and you can take it off the conveyor belt. And there's a big difference between those two things. Because if you put something on a conveyor belt and then go back to it, what do you expect? Nothing. The conveyor belt's moving, man. That's it. That flowed. So you can't write kind of the logic you can write with variables, going back and re-examining a place to update it in place and try to read it again. It flows. And so flow is a much more robust way to build a system. Data flow is a much more robust way than variables. So we want to emphasize flow over places. So program size matters, right? Smaller is better, right? This is one of the few areas where we have research, right? People have done research and said smaller programs have fewer bugs. It's just that simple. It doesn't matter what programming language it is. Smaller programs have fewer bugs, right? Bigger programs have more bugs, longer time to market. They're harder to maintain, and they're more brittle, right? But what I think is interesting is that there's two flavors of small. Right? A lot of languages focus on concision, right? Which is size in the small. Like how small is your if statement? How small is a function call? How tiny are your constructs? How much overhead, how much syntactic stuff is there? And there's a lot of languages that focus on that. Ruby and Python, and a lot of languages are actually very good at concision. But the bigger impact on a program overall, right, it's not moving from 42 characters to 20 characters. That only gets you 2x, right? The biggest thing is moving from more specificity, which bloats your program, to more generality, which shrinks it. That's the big payoff. That's the area where you're going to get a payoff much higher than 2x. So one of the other things I think we suffer from in object orientation is death by specificity, right? All the time. We have a new thing, we have a new idea, a new piece of data, boom, we have a new class. Get this, get that, get whatever. I don't care if they're value types, whatever. Right? It's just a glorified map, except you can't even use it as a map in Java. Right? There's no generic way to manipulate something that says get this, get that, get that. It's a new type, new language, it's got its own little vocabulary. Right? So you're going to have more code, you're going to have much less reuse, you're going to have more coupling. Right? Because essentially what's happening is every object has its own little language. My class, my interface, my own language. This is my biggest pet peeve I wanted to get away from this. When we started writing get this, get that, it's like there's no purpose to this. This is just life sucking. So let's look at life sucking. This is just a tiny part. I actually skipped. This is just the servlet request, and I have a little bit of HTTP servlet request, which really doubles the size of this thing. But my question to you is, how many maps do you see here? We're like, give a name, you get a value. I got one. I actually can't do the auctioneer thing. How many you got?
Looks like there's 1 or 2 submaps, like parameter names, parameter values.
Yeah. All right, so first of all, this game is hard, right? There's some. I got 3 inside, and the overall thing is a map too. So I got 4 right off by picking it apart. What's really interesting is look at these map interfaces. They're all ad hoc. Guess what else? They're all different. One has setting. One you can actually get the map. One you can get a list. Some you can get out with types. There's 4 different maps in this one class. This is crazy. Right? In Clojure, we just use maps. Right? This stuff came over wire in HTTP as text. How did we turn it into this? What happened? What happened? Why? This is crazy. Now, who can? I told you the curly braces are maps. Who can see how many maps? 1, 2. You see all the maps. Because they're still maps, right? If you're going to write code that manipulates that other stuff, every single line of code you write is going to be special. Has to, use whatever Java X servlet blah. Right? And you're writing code explicitly to this thing. If there's another way to do HTTP, not that there is, servlets are probably the only way to do HTTP. But if there was another way to do HTTP, will you be able to reuse that code? No. It's all written, it's all hardwired to this person or person's idea of like what an HTTP request is. Right? So yeah, okay, there's a tiny little benefit, right? Dot works in your IDE. Woo! Oh my goodness, because I could never remember that. So I bet something better happen when I press dot, because I'm doomed otherwise. Of course, I could look at the HTTP spec and like we could agree on these names, and I just don't get it. You can tell a kid not to put a spoon in a blender and turn it on, and like they will remember that for their entire lives. They will never make that mistake. But grown-up adult programmers, like we need protection, right, from this stuff. But the protection we get is really minimal. What's the cost? It's huge, right? That's an inconsistent interface. It's incredibly idiosyncratic. The interface is huge, so if you wanted to like have a second implementation, get to work, right? There's a ton more code to consume it. You can't use any of the libraries you already have, right? With the Clojure version, all the map code, like I said, those hundreds of functions, they work on this. You can create this with them. You can read this with them. You can merge 2 of these with that. You have no new code to manipulate this. No new code. All the functions you already know manipulate HTTP requests as soon as you represent them as data, which they were, by the way, before we mapped them. Right? The testing, right? It's easier to test data. Can you make a program that makes this? Yeah. Can you make a program that makes one of these? Yeah. Okay, and the other problem is your typical Java program has 2 to 3 orders of magnitude more of that. More of this, right? 100 classes, a couple of hundred. How many people have programs with more than 1,000 classes? Yeah. That's a party. All right. So Clojure programs are smaller in both ways. They're more concise, and they support generic programming, because we just program with these data abstractions. We represent information as plain data. So, this is always the biggest reservation. I love my types. I like my dot. I like my IDE. I can't deal with something other than that. And it's true, right? If you have the types of Java, right? Not fancier types. Fancier type systems can do more. But if you have the type system of Java, you can catch typos and passing ints when you're supposed to pass strings. But it's really likely that your tests or your REPL interaction is going to catch that stuff. That is not a quality metric. That is not sufficient for quality. It's part of quality, right? No typos. Right? But it's not sufficient for quality. Right? The quality is in all this other stuff. You have, what did we say? We have no way to deal with state management. We're encouraged to write highly coupled programs. We're inflexible. We're not meeting the customer stakeholder quality metric at all. In fact, we're pointed against it time and time again. We're pointed at the wrong thing. And because our code is so huge, we can't even really understand what it does anymore. So the biggest source of bugs in programs, which is misconceptions, right? Everybody gets it wrong. I talked to the stakeholder, they told me this, I didn't think of one of the situations when I wrote the program. That's the act, those are the real bugs in programs. Right? Everything else are superficial bugs. Those are the real bugs. They're harder to see. So I think these default idioms are a big win. I'm not going to spend much time on this, but it was interesting to me because I always like to look up words. What does economic mean? And it actually means relating to household management. Right? So the idea of home economics is kind of redundant. It's what the word means. And I would say that sort of a programming house is just like it's like a hoarder's delight. Everything, there's too much stuff in it. Everything is too big. We need too many people to do basic things. There's a lot more to Clojure. This was not a tutorial on Clojure. But the important thing is that most of it is in libraries. Clojure grows via libraries. The core is really pretty vigorously protected against growth. It's not like an experiment in language design. So the one other part of Clojure I'd like to talk about is polymorphism. And it just because it's another example of simple, I haven't talked a lot about simple, but one of the cool things about Clojure is that polymorphism is independent. In other words, it doesn't require inheritance. You can imagine, Clojure has something called protocols. They're a set of functions that work together. They're polymorphic on the first argument. So that's like the same kind of single dispatch you have in Java. So you can imagine them as interfaces, but they don't require inheritance. And the beautiful thing about not requiring inheritance is you can have a protocol and you can extend it to something that's finished. Something that Sun wrote a long time ago and is never going to change and certainly is never going to implement your interface, right? You can also take stuff from two vendors, right? Because what do we usually have? We have the framework problem. There's a privileged framework in Java, the one that comes with it. And people implement those interfaces. But if you have a piece of software from vendor A that has an interface and stuff from vendor B, like objects from vendor B, that you want to use, how do you get vendor B to implement vendor A's interfaces? It just doesn't happen. This was even worse in the C++ world, but in Java we still have this problem. There's a privileged framework that people implement the interfaces, and otherwise interfaces are parochial. They're small. So we have polymorphism in Clojure is a la carte, and that reduces coupling because you don't need to derive. All right, I know maybe Clojure seems more interesting now. So it's not just about technology, right? It's not even about these programming things. It's also about ecosystem and things like that. And the first thing that's great about using Clojure is that you get to keep connection to the ecosystem you already know. Not only the runtime and the deployment environment, but those libraries, right? The interop in both cases is extremely good. All those Clojure data structures I showed you, they all implement the appropriate Java, util, map, whatever. They all implement all the Java interfaces. You can just take one of those things you wrote in square brackets that was pretty easy and pass it to something that expects a Java util list that implements random access. Right there, works. Ready to go. Clojure is also very stable. I value that in Java. I think it's an important part of why Java grew, and Clojure takes the same approach. It's not like kids on GitHub hacking away, adding every new idea, or it's not a think tank experiment. It's made for production use, and it's very stable. All the programs from a long time ago still run. There are books if you wanted to get started. There's a lot of books now for Clojure. I spoke here last 5 years ago, and people had never heard of Clojure, and now there's plenty. There are tools. Oh, look. There's an IDE. That looks like Eclipse with code highlighting for Clojure and like structural nav. And oh, that's IntelliJ. Same thing. Breakpoints. Look, and you type and it starts popping stuff up. This is good. We're good. And you have a REPL down there, which is even better once you get used to that. There's a ton of tools in various areas. There are lots of libraries. That says 12,000 repos on GitHub. There are lots of users. The mailing list has almost 10,000 users on it. And they're all happy, nice people. I promise. No, they are. I think that matters if you've ever seen the old Lisp community. They weren't all happy, nice people. But Clojure users are happy and nice people. That's where Clojure's at. And RedMonk's where our language is at. Like, whoa, way up there. This functional Lisp. What is happening in the world? Look at it. There it is on the tech radar. Adopt. It's actually gone off the tech radar. They're like, of course, you should be using Clojure already. And they're right. Right? People are using Clojure already. A lot of people are already using Clojure. Banks use Clojure. Plenty of startups use Clojure. Plenty of analytics houses use Clojure. So people are being successful with it. So I think that's the short message for today. The idea behind Clojure is to get you to better and more flexible programs sooner. And the way it approaches that is by being data-oriented and simple. And I really appreciate your time. Thanks.
That was